All right. Hi, my name is Alex Panka. I'm in my third year of the NASA postdoc program in the Ionosphere, Thermosphere, Mesosphere Lab in the Heliophysics Division. My research focuses on modeling and analysis of infrared atmospheric emissions, specifically from the middle and upper atmosphere of planets, generally at pressures less than a couple hundred microbars. To properly analyze these emissions, we need to apply a special methodology called non-local thermodynamic equilibrium modeling, or simply nonLTE. For this talk, I'm going to explain why nonLTE modeling is necessary for simulating emissions of the middle and upper atmosphere of planets, as well as calculating the rate of heating and cooling rates needed in general circulation models. So the middle and upper atmosphere is seen as the gateway between the lower atmosphere and space. This region is sensitive to the solar influence as well as radiation from below. The absorption and emission of molecular bands in the middle and upper atmosphere affect atmospheric observations of other areas. Proper modeling of vibrational states of molecular gases in the middle and upper atmosphere is crucial for estimating the radiative heating and cooling rates needed for general circulation models. The analysis of infrared emissions can tell us a lot about the state of the atmosphere. For example, by analyzing these emissions, we can retrieve trace gas densities, temperature pressure profiles, and estimate radiative heating cooling rates. In order to properly analyze this infrared data, we must first understand and model the various vibrational excitation and de-excitation processes that the molecule undergoes. There are a number of energy transfer processes to consider. For example, we have to take into account the absorption of solar radiation, the absorption of infrared radiation propagating from the lower atmosphere, and the infrared radiation and absorbing and emitting among nearby layers within the middle and upper atmosphere. We also have to take into account collisions between trace gas molecules and main atmospheric constituents, such as molecular nitrogen and oxygen in the case of Earth, which can add and remove energy from these trace gases. And finally, we must consider the various chemical reactions that these gases undergo. So the interpretation of infrared observations requires proper modeling of the vibrational levels of trace gases. In the lower atmosphere, vibrational populations are defined by local temperature and follow the Boltzmann distribution. But in the middle and upper atmosphere, vibrational populations are not defined by local temperature anymore. Instead, we have a breakdown of local thermodynamic equilibrium, and a special methodology is applied called nonLTE modeling. So here's a summary of the differences between LTE and non-LTE in the context of planetary atmospheres. In the lower atmosphere, where pressure is very high, thermal collisions are the dominating energy transfer process. All other radiative and non-thermal energy processes can be ignored in what we call the steady state equation. Therefore, the velocity distribution of molecules is Maxwellian, and the vibrational and rotational population distributions, here represented as n, follow the Boltzmann law, which is controlled by the kinetic temperature. So this T here in this equation, if we know T, which is the kinetic temperature, we know the vibrational and rotational distributions, population distribution for each of the trace gas molecules. Further, rho vibrational lines have Doppler and Voigt shape, and source functions used in the radiative transfer equation are Planck functions and are also governed by the local temperature. In the middle and upper atmosphere, when the pressure and densities are exponentially lower, thermal collisions are no longer dominating energy transfer processes controlling the population distribution. Therefore, molecular vibrations are the first to depart from the Boltzmann law, and source functions are no longer Planck functions. So here, these n's, which define the vibrational population distribution of a molecule, have their own unique vibrational temperature, which describes its distribution, and it's no longer equal to the kinetic temperature. At even higher altitudes, molecular rotations depart from the Boltzmann law. And finally, in the most extreme cases, the Maxwellian distribution gets broken and lines no longer have Doppler shape. Now, for most of the studies that we do for planetary atmospheres, the Maxwellian distribution still holds, and and the rotational distributions we still assume are in LTE, while the vibrational distributions are in non-LTE. So we have a code package that we use to solve for vibrational populations under non-LTE conditions called ALI-ARMS, which stands for Accelerated Lambda Iterations for Atmospheric Radiation and Molecular Spectra. This code can be used to solve for non-LTE populations for a number of trace gas molecules listed here on the bottom, though we actually have more than what's listed in this figure. It solves these populations by iterating between the steady state equation and the radiative transfer equation. And once the populations are converged, it can calculate atmospheric emissions or absorption for several observing geometries, as well as estimate radiative heating cooling rates based on the derived vibrational populations. So here's an example of the effect that non-LTE processes have on infrared emissions for the case of CO2 in Earth's atmosphere. So the top left plot shows the complexity of our CO2 non-LTE model and all the various vibrational levels we incorporate, as well as radiative transitions and collisions between CO2 and its isotopes, as well as main atmospheric constituents. The figure to the right shows how the CO2 vibrational temperatures for certain vibrational levels deviate from the kinetic temperature. So remember from the Boltzmann formula down here, when a molecule is in non-LTE, its vibrational distribution no longer is governed by the kinetic temperature, but its own unique vibrational temperature, which are displayed here in red, green, and blue profiles. So these vibrational temperatures tell us how much these molecules are in non-LTE and at what altitudes. And you see in these cases, they are deviating from non-LTE starting at around 60 kilometers in Earth's atmosphere, which is just right in the mesosphere. And on the bottom here, we have the differences between emission models assuming LTE populations versus non-LTE populations. And so the left figure here is showing the CO2 15 micron band, while the one to the right is the 4.3 micron band. And radiance differences in both cases are at least a factor of 10 for the 15 micron band, and can be up to a factor of 1,000 differences in radiances coming from certain points of the atmosphere, depending on whether you assume the populations are in LTE or non-LTE. And this demonstrates how important considering non-LTE, how crucial it is to consider non-LTE in the middle and upper atmosphere. And this is not only seen on Earth, but around the solar system. As I show here, the non-LTE versus LTE radiances, now these are from a nadir geometry in all four cases, looking straight down at the planet. For Saturn, Jupiter, Venus, and Mars, the Saturn and Jupiter show the methane 3.3 micron band, while the Venus and Mars are the CO2 4.3 micron band. So for the Saturn and Jupiter cases, our non-LTE model reproduce, the non-LTE simulations in red reproduce observations taken by the Infrared Space Observatory in black. And so we have a very nice fit to the data. While assuming LTE throughout the atmosphere either underpredicts by about a factor of 1,000 in the case for Saturn, or overpredicts observations by about a factor of 4 in the case for Jupiter. And we see similar discrepancies on Mars and Venus as well for the CO2 bands. So in addition to properly interpreting upper atmospheric emissions of planetary atmospheres, we can also use the non-LTE model to estimate the radiative heating and cooling rates for such atmospheres. The two figures on the left show the different non-LTE and LTE vibrational populations for the CO2 15 and 4.3 micron fundamental bands. So this is just a specific vibrational level transition to the ground state. And you see the large discrepancy between the normalized populations of assuming LTE or solving for non-LTE populations. These populations now can be directly used in the heating cooling rate formula in the top right to calculate radiative heating cooling rate in the form of, in what we show, kelvins per day. And in the bottom right, for the case of Mars here, we show Heating and cooling rates calculated using non-LTE and LTE populations solved by ALI arms. A negative value, a slightly negative rate would signify cooling, while a positive rate signifies heating. And the LTE heating rate is clearly unrealistic, as in the upper part of the atmosphere it exceeds 1,000 Kelvin a day, while considering while solving the non-LTE problem, we have a heating cooling rate that gives much more reasonable values in black here. And therefore, it's crucial to use the non-LTE population to estimate heating and cooling rates for the middle and atmosphere of planet. And so our research team, the ones who developed ALI arms, has experience integrating an optimized version of our non-LTE heating cooling code. Sometimes solving for these populations can take quite a bit of time, and solving for heating cooling rates can, but we've optimized this process. And we've integrated our code into general circulation models. And studies have used our code to calculate heating cooling rates for specifically the CO2 15 micron band on Mars and Earth. And here's some citations. So in summary, if there is an atmosphere, there's a region where collisions are no longer fast enough to keep LTE, and non-LTE can be found anywhere. If neglected, the spectrum may be misinterpreted and wrong science is likely to be derived. Radiative heating and cooling calculations are strongly dependent on the vibrational populations of the emitted molecule, and if the vibrational populations are not properly solved, radiative heating and cooling rates can be incorrect by on the order of thousands to tens of thousands Kelvin per day. And that's it, so thank you.